Welcome to a session on carrier concentration in p-type semiconductor and discussion of Fermi level and variation of Fermi level with the temperature in p-type extrinsic semiconductor. Now first let us concentrate on calculation of carrier concentration in p-type semiconductors. Let Na be the concentration of acceptors in the material. At 0K, the acceptor atoms are not ionized and are at the level Ea. So what are these acceptor atoms? To form a p-type semiconductor, we need to dope pure semiconductor with impurity atoms. Which impurity atoms? Trivalent impurity atoms like boron. Here, this is the valence band of the pure semiconductor. This is the conduction band of the pure semiconductor. When these boron atoms are added, then boron atoms are having different energy levels. So this energy level of the boron atom is represented with the Ea. This dashed line is Ea, acceptor energy level, because it is accepting one electron from the germanium crystal. So that it is also called as a acceptor atom, and the energy level of that particular atom is called as acceptor energy level. You clearly observe this is a atom. Which atom? Boron atom, which is not ionized. And you can also see this, it is indicated with the minus sign. Why minus sign? As temperature increases more than 0 Kelvin, some of the electrons are accepted by these boron atoms. So after receiving this electron, this atom become a ion. As electron received by this particular boron atom, then consequently a hole will be formed in the valency band. In this way, holes are the majority charge carriers in p-type semiconductors. And one more point you need to observe here is, here as one atom accepting one electron, correspondingly one hole is formed. So the number of holes equal to the number of acceptor ions. Here you see one hole is formed, correspondingly there is a one negative ion is there. Here one hole is formed, correspondingly there is a one negative ion. Here you see these atoms are not accepting electron as of now, so that's why there is no negative representation of ion, and there is no formation of a hole here. So from this analysis we can write that number of holes in the valence band is equals to the number of acceptor ions in acceptor energy level. This is true when the temperature is very less or small. Now I am taking the same condition, P equal to Na minus. So what is P? Number of holes in the valency band. And what is Na? Number of acceptor ions. So we directly take this p-value as 2 into 2 pi mh star kt by square whole power 3 by 2 into exponential of ev minus ef by kt from intrinsic carrier concentration of valence band of intrinsic semiconductor. So in an intrinsic semiconductor, in valency band, the density of holes is this, 2 into 2 pi mh star kt by square whole power 3 by 2 into exponential of ev minus ef by kt. We need to convert this into the formula for p-type semiconductor, density of holes in p-type semiconductors. Let 2 into 2 pi mh star kt by h square whole power 3 by 2 as n into v. So the above equation will be converted as p equal to nv into exponential of ev minus ef by kt. We can calculate acceptor concentration as Na into exponential of ef minus ea divided by kt from statistical mechanics. So as P is equal to Na, substitute the value of P, substitute the value of Na by taking logarithms on both sides and rearranging, and by simplifying the above equation, we will get this formula. Ef minus Ea divided by Kt minus Ev minus Ef by Kt is equal to ln of Nv by Na. By simplifying the above equation, we will get minus Ev plus Ea plus 2Ef equal to Kt into ln of Nv by Na. By rearranging this equation, we will get Ef equal to Ev plus Ea divided by 2 plus Kt by 2 into ln of Nv by Na. So if you reverse this value, that means Na by Nv, we will get a minus sign before this plus. So the final value of Fermi energy level EF equal to EV plus EA by 2 minus KT by 2 into ln of NA by NV at t equal to 0 Kelvin, which means put t equal to 0 in this equation. So it left as EF equal to EV plus EA divided by 2, which means that Fermi level lies exactly half of the way between EV and EA, which means that here you can see. So this is EV and this is EA. EV is the highest energy level in valency band and EA is the acceptor energy level. So you can see, so the Fermi level at t equal to 0 k lies exactly half of the way between EV and EA. Now substitute the value of EF from equation 12 in equation 8. So we got EF value from this equation. Substitute this in this equation. P equal to 2 into 2 pi ms star kt by h square whole power 3 by 2 into exponential of EV minus EF by kt. Substitute this EF value from equation 12 in this equation. So now it will be turned as P equal to 2 Na whole to the power of half into 2 pi ms star kt by h square whole power 3 by 4 into exponential of EV minus EA divided by 2 kT. So from this what we can conclude is P is directly proportional to Na to the power of half, which means that density of holes in valency band of a p-type semiconductor is directly proportional to the square root of acceptor concentration. This is true at low temperatures. At high temperatures, intrinsic behavior predominates and acceptor concentration become insignificant. Here you see, with increase in temperature, EF decreases slightly as per equation 12. Here you concentrate on equation 12. If T not equal to 0, little bit high temperatures, what happens? T naught becomes 0. So the equation becomes EF equal to EV plus EA divided by 2 minus of something. So something is subtracted from EV plus EA by 2. So EF value get decreases. The same I shown in this figure. You see, as at T equal to 0, the Fermi level lies at EV and EA, middle of the EV and EA. As there is a slight increment in temperature, there is a slight decrement in Fermi level. As temperature increases, Fermi level decreases since more acceptor ions are ionized. At a particular temperature, all the acceptor atoms are ionized. So here you can see, as temperature continue to increases, all these acceptor atoms got the electrons. Simply all the atoms, boron atoms got ionized. Now the further temperature will be supplied to valency band. Now what happens, covalent bonds will get breakdown and directly that electrons rises to conduction band. So as conduction band and valency band having electrons and holes, this is the behavior of intrinsic semiconductor. As temperature becomes more and more, what happens? A large number of covalent bonds get breakdown in valency band. Suppose 1 crore covalent bonds get breakdown, then obviously 1 crore electrons rises to conduction band, 1 crore holes are there, but the holes formed due to the acceptor ions become insignificant at that situation. Now obviously this behaves as an intrinsic semiconductor, because in intrinsic semiconductor the number of electrons in conduction band and the number of holes in the valency band equal. Approximately this p-type semiconductor behaves as a intrinsic semiconductor at a very high temperatures. The same behavior here I shown. As there is a slight increment in temperature, there is a fall in Fermi level. As temperature continue to increases, Fermi level rises, and at a very high temperature, it approaches intrinsic Fermi level, which means that even p-type semiconductor behaves as a which type of semiconductor? Intrinsic semiconductor. So thanks for watching.